Hola, team.
Hey, good morning.
I'm still living in the 80s. Jesse's girl in the background.
Nice.
Let's see. We got some cool stuff to look at today. Notability. All right, I'll turn it off. Grow up. Let's see. So we want to practice decomposing. We want to practice solving these guys. Let's see. I want to let you in on something. I think I'm going to let you in on something that's just kind of fun rather than do this from scratch. We're really doing, solving differential equations. Solving differential equations with Laplace. We're just continuing that discussion. But I want to show you something kind of cool. Like I would like to make up I'm a teacher. Some of your future teachers. I'd like to make up a differential equation that's going to give me complex roots. And not only that, I'd like it to work out really awesome. Like I want it to work out really clean. And so let's see. What I'd really like is for the R value to be, I don't know, how about 2 plus or minus 5i. Like that'd be awesome if it worked out like that, right? Instead of, some ugly answer like 3 plus or minus the square root of negative 97 over 19, which would be 3/19 plus or minus the square root of 97 over 19i. Like that would be no fun, right? So I want it to be 2 plus. So how do you pull that off? Well, what's the original equation that would have came from? Well, think for a second about this. If I wanted it to just be 2 and 5, isn't this, if I wanted R to be 2 and R to be 5, isn't that what it would have needed to factor 2? So then can't I multiply that out and get R squared minus 2R minus 5R minus 5 times minus 2? And so if that was my auxiliary equation, wouldn't that produce those nice clean R values? Well, this isn't any different. In other words, I need this to be R minus 2 plus 5i and R plus 2 plus 5i. No, wrong. It's always minus. Except for the second time, this is minus. So that's no different. I just need to multiply that out. So let's see, what do I get? R times R squared. Actually, I think I should multiply that out a little more. Or you could say R minus 2 minus 5i, since I have to distribute that negative. And then R minus 2 minus a minus 5i would be plus 5i, and maybe that'll be easier to multiply out. So then I'll try to do this fast. R squared minus 2R plus 5ir. And then I start with negative 2 minus 2R minus 2 times minus 2 is plus 4, minus 2 times 5i is minus 10i, and finally negative 5i times R would be negative 5ir. Negative 5 times 2 is positive 10i. And negative 5 times positive 5 is 25 minus 25i squared. Well, do you notice some cool things about this? Notice there is a minus 5r and a plus 5r. There is a minus 10i and a plus 10i. So it means all the I terms dropped out, except for this I term, but that also drops out. Why does that drop out? Come on, it's not that early. What's I squared equal
Turns
to?
into a positive 25. I
Yeah,
squared is
squared
equal to
is-
-1.
I squared is -1, and -1 times -25 is positive 25. So I get r squared minus 2r minus 2r. And then I have a +4 and now a +25. So there. I need a nice auxiliary equation like that in order for that to happen. Okay, so you say, again, that was all just kind of an interesting freebie. If I started class by saying, okay, let's solve this differential equation. You wouldn't have thought anything of it, right? Until you just got going. But this is kind of cool because we already know that how that's going to come out. But let's go ahead and work through it now. So what we want to do is see if we can solve this using a Laplace transform. And this will be the case that, you know, what happens if there's sine involved in cosine. And again, we don't know that yet. I mean, if we're lucky, as we said, this is just going to factor to r minus 2, r minus 5, and then it'll be easy. But okay, so we launch into this and we say, all right, let's do what we always do. Let's take the Laplace transform of both sides. So, and I hinted at you pattern hunters that, you know, there's some shortcuts to this, but this is the kind of work I'd like to see on a test. So what happens with that? Let's see, wasn't it s squared? I'm going from memory here, times the Laplace transform of y. And the s went down a notch, so from s squared to s to the first. And then we take the derivative of the integral. So this would now be y. And then s goes down another notch, so there's no s's. And then we take yet another derivative. And so there's our, from memory or from the pattern, but you know, again, you should be checking your note sheet for that. That's the Laplace transform of y double prime, and the Laplace transform of -4 y prime, you know, from yesterday would be -4 multiplied by the Laplace transform of y prime, which also starts out, well, not with two s's, since this is just a first derivative, but with one s. And again, it's always the Laplace transform of y that's next. And again, we move down the line. Okay, so now that there was one s and now there's no s's, s to the 0. And I take the derivative of that integral, which gets my y out of there. And so that's my that's my first derivative. And then of course the 29. So let's write out what we've got. So we've got that, and then -4. I'm just distributing the -4 now. -4 s Laplace transform of y. -4 times -y of 0 becomes +4y of 0. And finally, we have the Laplace transform of 29y, which is 29 times the Laplace transform of y, and that all equals 0. Again, it's not because it equals 0, it's because we have to take the Laplace transform of the other side, and the Laplace transform of 0 is 0. So, and you know, today we'll get into what happens. We're still doing homogeneous problems, so you know what happens if it's not 0. Now, let's see, I don't think I'll take the time to do this, but let's go back and, you know, throw some initial conditions into this just so we can proceed a little faster. So I don't know, y of 0 is equal to, my 5s look like s's, so let's not do that. Let's do 2, and y prime of 0 equals 7. I'm hoping this is starting to get good, simple and familiar to you. So then I go back and say, okay, cool, that's a 2. Y prime of 0 is a 7. Y of 0 is a 2, and that's it. And so now what do I have? Well, notice your Laplace y terms. This doesn't look very good. I should probably write plus 29 there and get rid of it over here because it looks weird. So we have our Laplace terms. And so we need all those together. And again, the cool thing is we can factor the Laplace transform of y out of there, basic algebra. And what that leaves behind is s squared here and minus 4s there and plus 29 there. And as I pointed out yesterday, it's like, hey, that's a pattern we'd see every time. That's the auxiliary equation. It's no coincidence, if you will, based on the original problem that that's what happened. And so I could skip all of that stuff in green if I was kind of in a rush. Well, I could skip all the stuff in green except for these things. I want to highlight that. But, you know, I've also got these things that were not. They were not Laplaces, and so they've got to get out of there. We've got to get those over to the other side. So that's fine as long as I say, great, well then there's a minus 2s there. I'd have to add that to the other side. And then there's a minus 7, and it looks like a plus 8 on the left side, minus 7 plus 8, so that's a 1. And if I subtracted that to the other side, it'd be minus 1. I think I got too much of a hurry there.
Doug, since we're keeping the 4, is that the same thing as just divide? If we just divide it by 2, is minusing 8 same thing as dividing by 2?
Say that one more time. I can't follow.
So it's plus 4y to the 0, but the y to the 0 is 2, so that's the same thing as 4 times 2.
Yep.
Oh, I see. We're keeping it 29. My mistake differed a little bit. Sorry about that.
Yeah, the 29 with the plus y, and I basically had an 8 here, and I had a minus 7 there. So I just put those together as a positive 1 on the left side, and then subtracted it over to the right side. And so here we are again. And frankly, I don't want to say that that was easy, but that's a pattern we're going to see every single time. What we just did right there, as long as we're careful and don't make any algebra mistakes and so forth. That's a pattern we're going to see every time. And so here we are, like now, if you will, I don't know if I want to say the word pain, but now the pain starts, because it's like, how am I going to decompose that? Well, why is this particularly nasty? Why is this different? What's going to happen when you sit here and say, okay, well, I don't have anything in my Laplace table that looks like this. And so what we saw was we really would like to factor this. And so I'm sitting here with this expression. I'm thinking, okay, cool, s squared. I know how that factors, s times s. But then all of a sudden I ran into a roadblock, right? Roadblock is, that's a 29. That's a not composite, but prime number. And so it's 29. Like the only choice I have is to put 29 and 1, and it could be minus minus or plus plus, but it's like, that's not going to give me minus 4s. So it's like this thing doesn't factor. So now we're really stuck. Do you agree with that? So what am I supposed to do? And again, I'm always trying to teach you this from a different perspective. Oh, that's right. I forgot I got to show you that cool thing. I'll show you that next. So I don't see anything on this sheet that just has kind of a garden variety quadratic on the other side. In other words, what I wish I saw over here was something like, s squared plus as plus b or something like that. I wish I saw that over there, but I don't see that anywhere. It's like, no.
Don't you have that with the sign? But if a was 0.
Yes and no. So that's a good observation. So isn't that kind of close here? If a was 0, though, wouldn't that be s squared plus b squared? Yes. But notice we need an s term. Like we also need because our problem had that this time. Does that make sense?
Oh, okay. Yeah.
if a was 0. Now, what if a isn't 0? What if a is like 3? Let's just play with this for a second. What if this was like s minus a was 3 and b was like 7 or something like that? Well, couldn't you multiply that out? Wouldn't that be s squared minus 3s plus 9 plus 49? So isn't that s squared minus 6s plus 58? Like, doesn't that kind of look like what we have, except it's not in the right form? Like, notice the a, which I picked to be 3 just randomly, and b to be 7. Notice the 3 and the 7 are not really visible down there. Like, I can't tell that there's a 3 and a 7 there. And yet, why is it important to know 3 and 7? Well, notice that's the part of the exponent. The a is the part of the exponent for e, and then the b is the part of the period, I guess you could say, for sine. So it's like I need to know those, but that is exactly our way out of this. In other words, could we get it to look like that somehow? Is there some way we could get, so that actually is, this actually is quadratic, and actually I guess so is that. Those are both actually quadratic, but they're just in kind of a different form. And so that's exactly what we're going to have to do here. Like, it didn't factor. That doesn't mean it's impossible. We got to get it to look like that. So how are we going to do that? Well, this is something you have played with from time to time in an algebra class. But the question is, how could I do that? What do you wish this was?
Well, I'm guessing we're going to get sine or cosine somehow because it's complex roots.
Yeah, and that's kind of the key is we do have a quadratic here ultimately in this expression. And if we can get it to look like this, then notice it indeed is going to have an e and a sine. So this is the one we're looking at. Like, it doesn't look like that now, but we actually have a shot at getting it to look like this. That's kind of the key. Now, in your case, you knew that it had a complex answer. And, back in the rules for solving, back when we did this kind of this way, we said, oh, look, when we found the roots, they were, it's 2 plus or minus 5i. We haven't seen that yet. We will in a minute, but it's 2 plus or minus 5i. And then we said, oh, okay, well, if it's that case, you have an e and a cosine and the e and a sine. And so do you see it already beginning to happen? In other words, this is the only one we have a shot at it looking like. It's going to have to look like that, or maybe like this. That's the only shot I've got, but it doesn't quite look right now. Well, notice this right here is s minus a squared. In other words, a perfect square. The only time something's a perfect square is when, let's see, what if this was a 6s? If I wanted that to factor to be a perfect square, dig deep into your algebra knowledge, what number do I wish was right there?
A 9.
A 9. Because then it would factor to s plus 3 and s plus 3.
Are we going to try to complete the square?
That's exactly right. And so this is a technique that it's popped up 3 or 4 times in the course of your algebra knowledge called completing the square. In other words, I need it to look like that. Now, the cool thing is what if this wasn't a 9, but it was an 11? Well, your first thought might be, well, now it doesn't work anymore. But can't you think of that as just being 9 plus 2? It's like move the 2 off to the side. That's what we're going to do. And yeah, the mathematical way of saying that is complete the square. Do you agree that in our problem, we wish this was a 4? Because then that would factor to s minus 2 and s minus 2. Now, is it a 4? No, it's a 29. But can we just leave the rest of it over there? So that now we can say this thing is 2s minus 1 over s minus 2 times s minus 2 for this part of it, and then plus 25. Do you agree that's starting to look like what we need it to look like? Except for notice it's kind of important, if you will, that this number needs to be written as something squared. In other words, we have a 25 there, but it's important to rewrite it as 5 squared because our b then is 5. So this is kind of looking right. So we actually got that. We got it to work. But notice what's on top now. This is where the problem comes in, or part of the problem.
Yeah, we're
Notice,
gonna have to split them up and do partial fractions.
yeah. Notice up here, there's no s's up there. And not only that, what has to be up there for us? It's not just any old number. It's like whatever that number is. Like for us, that's a 5. And so that means there's got to be a 5 on top. It has to be a 5. Otherwise, this doesn't work. And then over here, same thing, like whatever this number is, for us, that's a 2, wasn't it? S minus 2. Then this has got to be a 2. And then this is just an S. It's not 2S. It's not 6S. It is 1S. Like exactly the same. We got to get it to look like that. And so we got a problem because what's on top of ours? We have a 2S. We don't want a 2 there. That's not good. We need just an S. And then we need a 5 up there, and there's no 5 in sight. This is not good. So let's think about that. I'm gonna bring these guys over so we don't have to keep going back and forth. I'd like to just give you a little bit of time to stare at that. Didn't I just take a picture of that? Where did you go? Oh, I guess it's right there, plain sight. How can we do that? We certainly can't just get a 5 up there because there's an S up there. So, part of me wants to say, well, we're not going to be successful getting it to look like this one because ours has an S. But this one has an S, and so great. Maybe I could get it to look like that one. Except for it's got a 2 up there. It's 2S, and so I'm going to get rid of that.
Can you just split up the fraction into or should you leave it as 1? Like as 2
Yeah.
the denominator minus 1 over the denominator, then you would have well, that
Yeah,
would
you
not
can.
do it either though.
That's a good first thought. In other words, this is a fraction. In other words, man, my S's look like 5s. So that 2S could be over the top of our denominator minus 1 over the top of our denominator. Like that would be maybe helpful, except for, again, the problem is, well, dang, that's not a 5. It needs to be a 5. And then, this S is not alone. Now remember, because there's a 2 there, that's okay, because remember we can pull the 2 out front. But then that leaves an S, not an S minus. And again, it's not just any old number. It's got to be S minus. Well, notice there's a 2 there. The RA is 2. In other words, that needs to be S minus 2. It has to be S minus 2.
We can add a -3 to that in the beginning and get 2s minus 4. Then if we pull out a 2, we're going to get s minus 2 for that top thing.
So your idea is what, Ben?
So if we somehow add a -3 to that top thing, we'll get 2s minus 4. And that means we'll have to also, yeah, subtract a -3 and then also added a 3 to that.
Good job. In other words, so do you understand what he's saying? He's saying if we, like he said, somehow, like, 'cause it's like, I can't just decide to subtract 3. But if I could somehow subtract 3 so that the top was 2s minus 4, then I could actually factor a 2 out and then it would be s minus 2, right? And we don't care about this multiplier because it can actually come down front, right? Is that a good idea or bad idea? Or is it like, that'd be nice, but you just don't get to do that?
I think it would work. We kind of did that with the denominator.
So how are we going to fix it? Because you can't just decide to subtract 3. How can that be okay to do?
You have to add 3 back in there.
Yeah, that's not terrible. Can't you just say -3 plus 3? Let's try that. That idea seems to have some merit. So we are saying then we're going to take our 2s minus 1 and we're going to say -3 plus 3. So that's okay, right? Over our denominator, which I'll now rewrite as s minus 2 squared plus 5 squared. And so again, we're doing the same thing we've been doing. We're just sitting here laboring around trying to get it to look like something in the Laplace table. And so is this okay then to say, all right, well, now that's equal to 2s minus 4 over our denominator. But then it would also have a plus 3 over the same exact denominator. Is that okay? Remember, I'm just unadding fractions, right? They have a common denominator. Is that okay? Number one. Number two, is that helpful?
Well, it didn't get rid of the 2s.
You
Yeah.
can factor
So
front because of the linearity of the Laplace operator.
so this becomes 2s minus 2 over our denominator. And this part of it right here looks exactly like it's supposed to now. Doesn't it look exactly like that now? And it's okay that there's a 2 out front, because remember, we can say, oh, 2 times something, fine. So that actually is 2 times the Laplace transform of s minus 2. So a is 2. So that was the e to the 2t, e to the at. And then it's the cosine of bt for sb is 5. And so that actually worked. But is this a dead end? Because notice this number is not the correct number.
Yeah, we have 3 different numbers over there. We just need 2 different numbers.
What do we need to be up there? Whatever that is, that needs to be the same thing. We need a 5 up there. That would have been really lucky if that happened to be a 5, wouldn't it? So we certainly can't count on that happening, but we were unlucky. So does that mean we got to go do something else? Is there a way to fix it? Is there a way to make that a 5 somehow? Again, it's not going to work to say +2 minus 2, because if we say +2, then that will be a 5, but then we'll still have a -2 to deal with, and it won't go away. Are we stuck? Or does anybody have a good idea?
You gotta go +7 minus 7. And just keep doing that all the way until it hits 5. Perfect.
We can do it, but you just got to multiply by something. Think about that. Remember, it's okay to multiply by stuff or to factor something out. what could I factor out? Now, you might agree with me that if this had been a 10, that wouldn't have been too hard. Do you agree with that? Because couldn't I just take a 2 out front, just like I did on the other side? Oh, it's 2. 2
Okay.
times.
Could you divide out, what was the number up there?
We need it to be a 5 because it's got to be an exact match.
So
Whatever's right here.
could you divide out 3/5? And then would that leave a 5 there, or maybe not? Maybe it's some other fraction like that. I don't know.
You're exactly going the right direction. Like just because it isn't nice, just because it isn't 10 or 15 or something really nice and easy. Yeah, so what is it?
It was 3/5. He was right.
3/5? Let's write that out. So if I took 3/5 out front, then is that true? It is true, because if you multiplied 3/5 times 5, don't you get 3? So like we didn't do anything, like it's still 3, isn't it? We just factored something out front. We factored a 3/5 out of 3. Doesn't feel very good, right? But so that actually does work. That was not a dead end. So this right here is the Laplace transform. And notice it's identical. In other words, it's the same exact statement. The A and the B are in the same exact location, except for it's just sine. So sine had a constant on top, and cosine had an S and a constant on top. And it's kind of cool that, this constant matched that constant, whereas with cosine, that constant matched that constant. It's kind of neat. So that's identical. In other words, it's still e to the 2t, and it's still the sine or cosine of 5t, but this time it's the sine. Wow. Okay, so wait a second, I'm lost. What were we doing again? Remember we were saying we have the Laplace transform of y equals this stuff here. And now we were able, by completing the square and some pretty creative factoring and messing around and so forth, we were able to produce a Laplace transform for that. Well, coincidentally, or interestingly, it produced 2. Like it took 2 of them to do that. We had to kind of split it up into 2 different parts. So here's where we are. We are saying the Laplace transform of y equals this gadget plus this one. That's where we are.
Now, would you distribute the 2 in to both the e and the cosine, or just to the e?
That's a good question. Let me think about that for a second. Yeah, I mean, I think technically it actually does need to go inside. And that's because we need everything to be a Laplace transform in order to inverse Laplace transform.
Mm-hmm.
So, and you don't have to write it in there, but yeah, I'm gonna cross them out and kind of put them inside just so that you can see that thinking. Notice how it's the left side now. It's Laplace transform of junk equals Laplace transform of junk plus Laplace transform of junk. We like plus signs because all Laplace transforms are as integrals. And so now we're in a position where we can say, cool, let's take the inverse Laplace transform. What's that going to do? It's just going to, now that everything's Laplace transforms, then we can just get rid of them. And notice we couldn't do that back here. When we were here, we could say, yeah, let's take the inverse Laplace transform of the left side. But notice the right side isn't a Laplace transform. So we can't take the inverse of that. So we had to work at the right side to get it to be a Laplace transform, or a combination of them, as happened with us. so that we can do that. And so now it just gets rid of all of those Laplace transforms. So I can say, okay, well then y equals 2e to the 2t cosine of 5t plus 3/5 e to the 2t. And of course, you're more than welcome to factor e to the 2t out and not write it two different times. That's fine. Notice you're not surprised by something. And remember that r was equal to 2 plus or minus 5i. Remember how we made that be the case? Like I designed it to do that. And remember this was kind of our alpha, which went with e. And this was our theta that went with sine and cosine. Before, like you see it produced the same answer that it would have had we done it the other way. Isn't that kind of cool? The only thing we didn't, do was the 2 and the 3/5. But remember how painful the 2 and the 3/5 were to get, by the way? Remember how we knew it was y equals c1 e to the 2t cosine of 5t plus c2 e to the 2t sine of 5t. And then what do we have to do to figure those two things out?
Plug in the initial values.
Yeah. So our initial value, y of 0 was 2. That wasn't too bad. But why is this one terrible?
Because you got to take the derivative, do
Take the
parts.
derivative. Yeah. And why is the derivative such a pain in this case?
Because you got e's multiplied by sine and cosine.
Yeah, you got junk times junk. Therefore, that's a product rule problem to take that derivative. And so notice it's kind of interesting that we got 2 and 3/5 and we didn't have to do any of that. I mean, so again, there's kind of pros and cons to this as a technique, but notice those just kind of showed up because we plugged in the initial conditions clear back at the beginning of the Laplace transform, didn't we? And they were kind of easier to plug in there. So that's kind of cool. So isn't this kind of crazy that it literally produces the same exact answer? It works every time. It works in every situation. We didn't have to know going into this that it was kind of its auxiliary equation, if you will, had imaginary or complex answers. We didn't have to know that going in. But remember, when did we discover we were in trouble? We discovered right here we were in trouble because this time the bottom didn't factor. Does that make sense? And the fact that it didn't factor, notice we didn't have to go do the quadratic formula and get 2 and 5. We didn't have to know that the solution to that was 2 plus or minus 5i. However, the fact that it was 2 plus or minus 5i, which we could have chosen to go find out if we wanted to, that would have told us something about our final answer, wouldn't it? Like the fact that there's a 2 here and a 5 here, that is not a coincidence. We could have known that that was going to happen a long time ago. How could that have helped us? Like if you want to take that approach, how could that have helped you during this phase right here where we were kind of suffering with, how do I complete the square and, how do I get that to look quite right? I mean, would it have helped, if you will, since effectively there's the 2 and there's the 5 right there? Like you already kind of know how that's going to play out. Like that's how it's going to look when you complete the square based on the complex answer 2 plus or minus 5i. Could that have helped if you're sort of not as good at completing the square?
Oh yeah. It'd be good to go down the other path that we learned before, the first few steps, just to see the roots so that you know what you're looking for.
Yeah, so that could help. And so pay attention to that. So it's interesting that if you look at the auxiliary equation that's always sitting here kind of back when you start, because you divide by it, it always ends up in the denominator on the other side. And being in the denominator, that becomes kind of the challenge is, what is that going to turn into? If I can factor it into two simple things like s minus 3, s plus 7, if I can factor it to something like that, then I know my answer is going to split up and then become an E sort of an answer. That's what it's going to split up into. So if it factors nice like that, And of course, on a test, I'm going to work hard to make sure it factors nicely. I'm going to make it clean. So if that's the case, cool. And then we saw yesterday, if it factors nicely, but it factors to two identical things, that wasn't so fun. If it doesn't factor at all, meaning it's a complex answer, then we might know, or at least have an intuition that it's going to go down this E sine and E cosine route. Interestingly, it's kind of funny, but does it make sense that like we ended up with both of these, like we needed them both, in a sense that that's kind of cool that happened, given that that's what happened back when we were doing this by cheating. Remember, we used to just guess at this and say, well, here's your guess. Now we don't have to guess. That's kind of neat. But we have to work really hard to decompose this into something that one of our options on the table. That's what's kind of so challenging. And just as a quick side note, you may remember we never made this one ourselves. We never made that one. I just stole that out of the table, and we just said we knew it was equal to. But let's just take a second, because we have, again, 3 days to play with this. Where did that come from? Like, how would you get that? Well, remember one of our cool dodges. And by the way, there's a second cool dodge on here that I added something to. If you printed this yesterday, it occurred to me that this second cool dodge that I haven't shown you yet might have been hard to understand, so I added something to it. But anyway, what did this cool dodge say? It said, if you need to take the Laplace transform of E multiplied by, something else, can be anything, sine, tangent, t cubed, whatever. If you're multiplying E times your function, then what does that right side say? Can you understand what that's saying? It's saying all you have to do is take the Laplace transform just of this function. In other words, you just get to ignore that. Don't even have to pay attention to it. Just take the Laplace transform of the function itself. But then where there was just an S, you're going to replace it with S minus A. Isn't that what that said? Now we looked at that.
Is that because when you take the integral from 0 to infinity, you multiply by e to the negative st? Is that why that EAT goes away?
The reason it goes away is because the Laplace transform already had an E in it.
Yeah,
It already had an E in it. And so if you add another E, then it isn't like adding another function. What it's really doing is saying, well, if you add another E to the AAT to this, then isn't that really just one E to the A minus S? Now there's just, but then we said, well, we really want it to be negative. So if we pull the negative out in front, then that would switch this to S minus A. And so all that really happened then is, well, there used to just be an S there. Well, now there's an S minus A. So it doesn't add anything. So let's just for the fun of it, let's just use that really quick. So we made for ourselves, and you may remember that was extremely painful. I made for you in class this one. You, for your assignment, had to make that one. So what if we threw in here an E to the, I guess this is kind of a bad example, but an E to the 3t. Well, what that cool dodge that I just showed you is saying, hey, you don't have to redo this. Just use the one you already have, but then replace this S here with S minus 3. So isn't that, the letters are kind of screwed up since A got used down here instead of B, but you see that, hey, yeah, That actually wasn't that hard to make, thanks to that cool dodge.
I think you did show us that a while back.
I showed you the cool dodge. You think I even showed you this?
I think you showed us replacing the S with the S minus A.
Yeah, I know I showed you this cool dodge. I just
Okay,
not
okay.
sure how many examples I did of it. That's what I couldn't remember. So that's just kind of neat to see. As I said, it's kind of fun to not borrow this table, not borrow Doug's Laplace table, but to have your own, make your own these, build them yourself. That's just kind of a cool thing. That was yesterday.
Hey, Doug, for that second one where it was the Laplace transform of t times some function, would we, when we take the derivative of the Laplace transform of like a derivative, for example, like if we were to take the derivative of the Laplace transform of f double prime, if we were to differentiate that s squared times the Laplace transform of f, would we do like 2s times the Laplace transform of s plus s squared times the like the derivative of the Laplace transform of f? Like, if we denoted it like y of s, would it be like y prime of s?
Yeah, that's exactly what it'd be. Let's go ahead and do that really quick. I was trying to
Okay.
figure out like when I need to show this to you, and I just haven't kind of had a natural time to do it. But let's just do it right now really quick.
Okay, so we would use the product rule then, and then differentiate it, quote unquote, implicitly.
Yeah.
Okay, cool.
So see, here's one we didn't build. But let me write a simpler version of that. Notice that's t to any power, but I'm just going to say n equals 1. So I'm going to say, let's find the Laplace transform of, no, let's actually not do that one. Let's do this one instead. Let's do this one right here. We never did that one, right? So there's one that we never made. And you may be able to appreciate that's going to be nasty. Do you understand why? The reason is because we're going to have to take t times the sine of at, and then we always multiply by e, the negative st, and we have to take that integral. That's like integration by parts kind of on steroids, right? Because we have 3 things in there now, not just 2. And so that's really messy. That's really ugly to do that. So is there a way out of that? Well, what this dodge over here is saying, hey, good news. If you don't have e times a function, but you have t times a function, then what can you do instead? Well, if you take n, which in our case was 1, it was t to the first power, then you take -1 and raise it to whatever that power was. So what that does is kind of mess with the signs here. In other words, if this was 2t squared, that'd be -1 to the 2, and that'd become a +1. If this was t to the third, that'd be -1 to the third, that'd be a -1. This was t to the fourth, that'd be -1 to the fourth, that'd be back to a +1. So there's a sign alternation that's taken care of. And then what this is saying is kind of the same thing as before. In other words, all you have to do up here is take the Laplace transform of the other function, just ignore the e. This is saying the exact same thing. Take the Laplace transform just of that function. Don't worry about the t, like boom, boom, gone. But what's this, n right here? Well, you got to actually take the derivative of that. So if we're sitting here, so let's just do it. So if I'm sitting here with the Laplace transform of t sine of at, and I'm thinking, man, that's going to be horrible. Look at that thing. Well, this dodge says, good news. All you have to do is take, since this is t to the first, you have to take -1 raised to the first power. And then you just get to take the Laplace transform of the sine of at. Oh, we already did that. It was that, right? So that's -1, and the Laplace transform of the sine of at is a over s squared plus a squared. Cool. Except for what else was over there? the number of derivatives. Oh, okay, so we're not done. We actually have to take the derivative of that. We have to take the derivative, one derivative of that with respect to s. What would the derivative of that be? Well, I'm going to rewrite it as a times s squared plus a squared to the -1. So we're taking the derivative with respect to s, and remember a is a constant. Well, to take a derivative of that, don't you multiply this down front? So that becomes -1 times -1, so that's just +1. And then you subtract 1 from that, right? Power rule. And then, because of the chain rule, you say times the derivative of the junk inside. The derivative of s squared is 2s. The derivative of a squared is 0 because it's a constant. So I guess since this is to the -2, it could go back to the bottom. And the 2as could stay up on top. That looks nicer, don't you think? Like no negative exponents. I think that looks a nicer answer. So there's the Laplace transform of t. Hey, we just did it. T times the sine of at. It's 2as over s squared plus a squared squared. That's what that dodge allows you to do. Now, all that is a shortcut. It's not as though you actually can't do integration by parts here. It's just that you would have to, and this would be fun, you'd have to kind of say, well, I'll make that entire equation my u, and then this equation right here will be my v prime. So it'd be something like that. So I just want you to be aware of it. I'm not going to go all the way with that, but that's what that's getting at. So basically what these two cool dodges are saying in short is if you need a Laplace transform of something and it's multiplied by e, then you can make your life simpler and not worry about the e and just worry about the other function. If you are taking the Laplace transform of a function and it's multiplied not by e, but by t to any power, then good news, you can take the Laplace transform just of f, except for you might have to take the derivative of that answer a few times before you're done. That's pretty cool. Honestly, I mean, as far as what we're doing in this class, I don't think you need to know those. Like, I'm not going to ask you, I'm going to ask you to build one of the simple ones, as I told you on the test, but not one of the complicated ones. It won't involve those two cool dodges, but it'd be wrong for you not to know those, or at least have seen them. They're kind of cool. Okay, now you need practice, but you now can solve all three cases of the homogeneous second order differential equation. In other words, you can do all of these cases right here. Number one, you can do all those. We've looked at an example of all three of those types, and so you can handle it if it's homogeneous. Now remember, if it's not homogeneous, then this is again a place where Laplace transforms really shine, because if it wasn't homogeneous, you sort of had to look and see what was on the right side and then prepare yourself a proper guess, right? And so if there were t's and e's over there, you had one type of guess. If there were t's, e's, and cosines, or maybe just cosines, remember here, alpha could be 0 and then there wouldn't be any, and m could be 0, and so all there was a cosine over there. But like we had a different set of guesses, right? We had the sophisticated method of guessing, and we had to pay attention, like what case are we in. But again, Laplace transforms shine, and why you see them in applied physics books and mechanics books and so forth is because this method means we don't have to pay any attention to any of that stuff. We just have to keep doing what we've been doing. So I'd like you to get a little bit of a head start kind of trying this. Now I'm going to make this one up at random, and so let's just see what happens. Maybe this will go into a disaster. What about the non-homogeneous case? And so I'm just going to make something up here. Y double prime.
Oh boy, here we go.
Here we go. This is going to be sweet. Let's see. I want to kind of make this up randomly. I'm not going to completely make it up randomly. You guys are my friends, so. But let's say there isn't a 0 on the other side, but let's keep it kind of simple for now. Let's say something like 4t minus 8 or something like that. I'm going to give you some time. No different. Just take the Laplace transform of both sides. It's just you're not going to have 0 on the right side this time. Laplace transform of 0 was 0, but the Laplace transform of 4t, well, look it up on your sheet. Laplace transform of 8, look it up on your sheet.
Are you going to give us initial values?
Yes. And I'm just going to make those up, which again is alarming because that could be terrible. Say y of 0 is 2, y prime of 0 is 5. See how far you can get into that now. And my question is ultimately kind of, is this different? Is it not different? Is it different worse?
Should we do the 4t minus 8? Should we do those separately?
Yes. And the reason is because there's a minus sign. And since the Laplace transform is an integral, that means we can do them separately. And so it'll make our lives a little easier.
Okay.
It's a good question.
Getting quite a mess.
Yeah, it's a
Yeah,
glorious bundle of nonsense.
my left side's kind of nice, but my right side's a mess.
Don't you have to divide the left side to the right side? And
Yeah,
That's-
yeah, that's what I'm doing right now.
that's when it became just a huge bundle of yarn.
So I don't think any made mistakes, but I tried to do it mentally. So it is no joke that there's no longer 0 on the other side, right? It's kind of creates an uglier kind of rat's nest to untangle over there, if you will.
You should get that 8/s. I got a 1/s for that. Oh, never mind. I see why.
Yeah,
How did
the
we
Laplace
get-
transform of 1 is 1/s, and then you multiply it by 8. Good job.
How did we get 25? Because I got 11.
That's 2s.
That's my S's look like 5s.
Oh, okay. My bad.
So do you agree with what I got? And I'm actually not asking that to make sure you're right. I'm also asking it to make sure I'm right.
Yeah, that's what I got.
Good, okay. And then of course I still have to divide by all that other stuff, right? And so this just feels like, whoa, man, I'm never going to be able to untangle that. And notice I didn't add that much to the other side. I only added 4t plus 8. Like I didn't add e to the 6t plus the sine of x, or I mean, it didn't get crazy. But here's a piece of advice. I would really like to add these together so they have a common denominator. And you'll see why in a second. Well, I mean, mainly it's because I just don't want fractions over the top of fractions. Does that make sense? So if I can make one fraction out of that, so I guess what would that be then? 4 minus 8s plus 2s cubed plus 9s squared over s squared. So then when I divided my auxiliary equation away, wouldn't I just have this? Remember, we're not actually as concerned about what's on top, but what we are concerned with is what's on the bottom, because it's what's on the bottom that we have to decompose into kind of a bunch of fractions that are added together to get them to look like Laplace transforms. And again, as I said the last couple of days, you can see why the book thought we better kind of have a chapter where they learn how to decompose stuff like this, because if you get here, you're going to get stuck. But it's like, this is where these messes come from. Now, just as a side note, before I wade into this, does it make sense? You would have, back in the days when we guessed at this, you would have said, oh, there's going to be a homogeneous answer to this. And then there's also going to be, well, because that over there is a 4t plus 8, there's going to be an at plus b answer as well, right? Wasn't that how our guess structured? So I'd have whatever my homogeneous answer is plus that answer, and then I would, take its first and second derivatives and sort of try to force it to work, and that's kind of what we did. So we're just kind of guessing, but just keep that in mind because we're trying to get to the same place without guessing here. So, man, that is ugly. Now, what's cool this time about our auxiliary equation that was not cool about the problem that I started today with?
It actually factors.
It actually factors. That's exactly right. I guess I'll have to write it down here. So this factors to s plus 5 and s minus 3, which makes our life easier. That's good news for us, in terms of just being like, let's be done and be lazy and so forth. This is good news. So from what I don't like is squares. I mean, that's kind of the idea with guessing. I like the fact that this just broke into an s and an s minus 3. I don't like this s squared, though. That's kind of a bummer. I wish that was just an s. If that was just an s, then I would have said my guess is a over s plus b over s plus 5 plus c over s minus 3. If this was just an s. But what we learned yesterday is because it's an s squared, that's not going to work. This won't work.
You have to do the as plus c over s squared.
Yeah, and you have a couple of choices. So in class, this is what we did. We said, well, if this was just 1 power lower, and notice that cool pattern, because isn't that what happens here? Like this is s to the first, and this is 1 power lower, s to the 0. This is s squared, so this has to have an s in it. So this was kind of our approach that we created in class, was you'll need that, but also everything below it. The book's approach, which is actually better in terms of speed, is to do this instead. Have your s squared term, but then also have an s term. And then the rest of the terms. Whoa. The book's approach to this is easier. Do you notice they're the same though? I'm going to take the book's approach because you'll see why it's easier in just a second. But since this is 2 terms up here, couldn't you say that's the same thing as as over s squared plus d over s squared? And then this cancels with this, and so you have a over s and d over s squared. That's what we have. So they both work. Now, the advantage is, though, notice we have 4 terms down here, and those all look like something in the table. You agree with that right now? This is an e to the 3. This is an e to the negative 5. Over s, we just saw that a second ago, some kind of a constant. And this is like some kind of a t term, right? Like that's nice. That's exactly what I'm going to have. Now, notice from what I said back up here, just kind of reminding you when we started this problem, there's going to be a homogeneous answer plus at plus an at plus b. Well, isn't that exactly what's coming out of this? We have our homogeneous answer right there. And then there's a t term and a constant term. Like that's exactly what we would have expected from back when we used to guess at the answer to these things. What I don't know, because I didn't look at it, is, does the book do a good job of helping you kind of discover this pattern, or do they just tell you this is what you do? And you're like, okay, you have no idea why. Well, of course, our job is to now figure out A, B, C, and D. Can you appreciate how daunting that's going to be? It's just algebra. And it's cool because we're not guessing like we were kind of back in the old days. But this is still algebraically really daunting. Do you agree with that? Because in order to get this green equation to be that orange equation at the top, I'm going to have to add all four of these fractions together to make it be equal to that. And that's how I'm going to determine my A, B, C, D. But in order to do that, don't I need a common denominator for all these fractions? And so, woo, here we go, baby. So that means this needs an s plus 5 and an s plus 3 so that it can have the right denominator. And unfortunately, that means top and bottom. Man, s's are bad for me. S minus 3. Got excited there. This next one needs an s to become s squared and an s plus 5 and an s minus 3, right? Needs all of that stuff. So I'm just going to pile them there because it's kind of cool to do it that way. And then what does the s plus 5 need? Well, it's going to need an s minus 3, but it's also going to need an s squared. And the s minus 3 is going to need an s plus 5 and an s squared. And then I would be able to add all these together. How quick are you at algebra? Can you do this kind of stuff in your head? In other words, can you multiply s plus 5 times s minus 3 in your head? Well, you don't have to. It's actually s squared plus 2s minus 15. We already did that earlier. But then all of that is multiplied by s. So that would be as squared plus 2s plus 2as. And then there was a minus 15, but now it's minus 15 times a. So that would be that first term. And then b times exactly the same thing, except for there's an extra s because it needed one. So there'd be a b times s squared, except for now it's going to be s cubed. And there'd be a plus 2bs, except for there's an extra s. And there'd be a minus 15b, except for there's an extra s. So all of this came from up here. All of this came from right there. And now this, of course, would be s squared times s minus 3, or s cubed minus 3s, and all of, I'm sorry, s squared, s cubed minus 3s squared, and that's all multiplied by c. So that'd be a plus c s cubed minus 3cs squared. And then lastly, this would be s cubed plus 5s squared, all multiplied by d. So that'd be plus ds cubed plus 5ds squared.
Wait, shouldn't we get a 3c also?
Yeah, I've got it right here, I think.
Okay, yeah, never mind.
And again, I've said this lots of times in my class, but it's like you can appreciate it's really easy to make a stupid mistake here, right? So on a test, just make sure, don't waste some paper, like make sure it's nice and big, make sure it's easy for me to kind of look, and all you, I mean, if you lose a squared, if you, the tiniest thing, I want you to think about this for a second, like look at the squareds. See how there's a squared there, and there's a squared there, and there's a squared here, and there's a squared here. Like those are all going to combine together to give us our 9s squared up here, right? But what if you accidentally wrote this as a 3? You see the problems that's going to cause? Because like now it isn't in there with the squareds like it's supposed to be, so it's going to screw up the squared answer. But then it is in with the cubed answers, and now it's going to screw up the cubed answer. And so this is a good place just to go really slow and kind of, you know, write everything out, be careful, and, you know, think about it. Don't do too much stuff in your head. So this guy came from here. And this guy, jump, came from there.
Hey Doug, I'm getting some pretty funky numbers. Is this supposed to be like nice and clean, like book problem, or?
Because I made
Okay.
it up, so it's going to be disastrous. And so I
Okay.
think
Okay.
it needs to be, and this is a good place for, you know, hopefully the matrix can do the work for us, but yeah, this would be a good place for me to take a little time and make something up that came out nice. So all of this I need to be equal to that numerator, right? So then I just start looking at all my, again, this is kind of cool because I'm not guessing. So be very careful, be very conscious. What I like to do with stuff like this is, you know, mark things out. Like I say, okay, 4. I got my 4. Where's my 4 coming from? My 4 is coming from my constant terms. S squared S. There's one. You like mark it out. Make sure you get all of them. Any more constant terms? Oh, that's interesting. That's it. So that means I could actually answer that right now. So to Connor's point, ooh, that's ugly. So that was kind of cool. I was thinking I was going to have to use a matrix, but there's only one constant in that entire expression. So, and again, I'm looking back over it now thinking, really? I guess that's true. Great. Okay, there was a minus 8s term. And again, notice I'm looking at s terms now. If you have colored pencils, it's even a good idea to change colors, but like there's 1, 2as. Notice I'm leaving the s's off. There's an s term. There's one, minus 15b. And that's it. And since I know a is negative 4/15, I'll be able to plug that in and find b. So I guess I'll just do that right now. Oh man, that's awful. Again, you should be cheating because like fractions should be boring to you. So what am I typing in right now? I'm going to type -8 on the left side, and then I have 2 times negative 4/15. So I'm going to have to subtract that to the other side. So I'm going to say -2 times negative 4/15. I hit divide, I get some crazy decimal. Then I got to divide by -15, divided by -15. I get some crazy decimal. I say math, convert it to a fraction. It says b is 112 over 225. Like I didn't work very hard for that. Is it because I'm not capable of doing it by hand? No, very capable. I just got better things to do. That's what you should be thinking. And again, I'm inclined to make a mistake too. Please point it out if you see that. I'm not going to sort of be satisfied I got this right. And let's not forget to check our work. Like a bunch of you didn't do this on the last test and it kind of cost you, but I'm going to go check this in Desmos when I'm done.
That's the b value I got too.
Oh, good. So what about our squared terms? Oops, 9s squared. So my s squared terms, there's a 9, there's one a s squared. There's 1, 2b, and there's 1 minus 3c, and there's 1 plus 5d. Wow, there's a bunch of those. Notice I can't do that one. I know my a and b, but this still has a c and a d, so I can't do that one. Then I go back and look at my cube terms, 2s cubed, so my s cubed terms. Then I should be able to just look up there and everything else should be cubed, right? Because I crossed it all out. So there's a bs cubed, there's a cs cubed, and there's a ds cubed. So I know A and B. And so what I'm going to do is take these and kind of move them over to the other side with those values plugged in. So again, I'm just going to type this in my calculator so I don't make a mistake. 9, I'm going to say minus A. Minus A. Well, A is 4/15, negative 4/15. So it'll be plus 4/15. And then I've got to subtract 2B. So I'm just going to say minus 2 parentheses 112 divided by 225. Looking at my calculator, making sure that's what I typed. I got 8.2711 as a fraction. Wow, baby, that is nasty. I got 1861 over 225. And the rest of the other side is still the same, 3C plus 5D. Second equation, I have 2 equals B plus C plus D. Well, B is 112 over 225, so I got to subtract it over. 2 minus 112 divided by 225. Convert that to a fraction. I get 338 over 225. So that second equation is 338 over 225, and that equals what's left, which is C plus D. So I've got now 2 equations, 2 unknowns. So you linear algebra people are much more comfortable in this world than those of you that didn't take 261 in the spring. But you've all done this before, so that you can't do this. And so I see that I could do that by hand. I could multiply the bottom one by +3 so that I could add the C's together. But again, I'm lazy, don't trust myself. So I'm going to the matrix, second matrix. Edit, I need a 2x3 matrix. What do I have to be careful about, you linear algebra people, when I type this in? Because I haven't written this very, very good. Do you understand that?
That all the C's are on one side, all the D's, and then equal sign.
Yeah, these are lined up and that's fine. But remember, this actually has to be on the right side. If you put it in the order that I have it written, it won't work. The matrix is a cool shortcut, but it only works if you use it correctly. So I'm going to put -3C plus 5D and then put 1861 on the other side. So I'm putting -3 and 5 and then 1861. Notice how much trouble this is just because, I didn't take the time to make something up that came out nice. Again, that would be, in my opinion, sort of criminal on the test to do something like this because it's just so little chance I'm going to get this right. So then I put 1, 1, and then 338 divided by 225 on the other side. And now it's all in. So I can say second quit, second matrix. This time math, reduced to echelon form of matrix A. I can convert that to fractions if it will, and it said it would. So I got C equals -19 over 200. And I got D is 115 over 72. Again, I'm not sure, unless, some of you might be keeping up with me and say that's what I got, or I didn't get that.
That's what I got.
But certainly if you're by yourself on a test, you're not really very sure, right? This doesn't feel very good. So, and I don't know about you, but this happens to me a lot when I'm doing math. It's like, I just got that answer and then I suddenly think like, no, wait, what did I just do? Like, where am I? What was I doing again? That green equation right there, we just actually figured out how to decompose that. So we're actually almost done. So A was my S squared term. So then where am I? I'm at this place. I can say now that the Laplace transform of Y is equal to A over S squared, 4 over -15 over S squared, plus B over S. B was 112 over 225 over S. Plus C, I forgot which one that was. C was the one that was over the top of S plus 5, plus -19 over 200 over S plus 5, and then finally plus 115 over 72 over S minus 3. Did I have that right? S plus 5, S minus 3, yes. And so the question is now, do you recognize those as pretty easy conversions to Laplace transforms? remember we wanted this, we need this up here to be a 1, right? Not a 4/15. So we have to say that equals the Laplace transform of, let's see, 1 over s squared was t, right? So isn't that negative 4/15 t? And we want this up here to be a 1 as well, 1 over s. The Laplace transform 1 over s is 1. Isn't that right? Or the, oops, wrong way.
Yeah, 1 is 1 over s.
Yeah, 1 over s is just 1, but then that's being multiplied by 112 over 225. So this is the Laplace transform of 112 over 225. And then the e terms, same thing. We, again, needed that to be a 1 up here. Every one of them, we wanted to be a 1. Isn't that right? Let's just go double check. Keep hitting the wrong one. Yeah, that's right. E, we needed a 1 on top, right? So we're thinking of it as a 1, but that's no problem. We just factor out the 19 over 200. So this is plus the Laplace transform of negative 19 over 200 times e to the negative 5t. Make sure you don't screw that up and put positive 5. That'd be an easy mistake to make, I think. And then plus the Laplace transform. If I take out 115 over 72, then that'd be e to the positive 3t. And so now I can take the inverse Laplace transform, and I think I'm done. I think I found
I was really
this is
hoping
my
that
answer.
Laplace transforms would be quicker in our guessing.
Yeah, and I kind of told you from the start, it isn't like, oh yeah, these are so much better. They're really not. I mean, frankly, this is slower. Like what we did here is in terms of speed, it was slower than cheating. And that's kind of the back and forth. We knew this equation would have an AT plus B, and we also knew it would have a homogeneous answer, right? We knew it was going to have those two answers based on the guess, but that was back when we had to guess at this stuff. So the cool part of this is we never guessed. We just went and made it happen. That's kind of cool. But it actually took twice as much time, I would say. So as I've told you from the start, I don't know if this is just automatically better.
This way definitely doesn't feel better, but I like that it doesn't require, I feel like I'm like doing a puzzle on the other ones.
It's funner. This one's funner.
Yeah, it's interesting because there's actually a lot of room for kind of your own opinion on this. I think I always kind of say I don't think everybody in class is going to think they're the same. Everybody's going to kind of have their own take.
Like, I don't
Let's
think
see.
I would have ever come up with Ben's idea to subtract 3 and then add 3 after that. Like, I don't think that ever would have come to me, but that isn't an issue with this other way. Even though this other way feels way worse, like I can at least, I know where to go.
Yeah, and that's an excellent point. That took a lot of creativity, didn't it? So yeah, it's not for sure. So you're all seeing Desmos. Let's see, how did we check this again? We said, I'm kind of remembering this myself because I don't really remember either, but the original problem was, so we're saying we think the answer to this is f of x equals, I'm trying to remember how to do this. I have to kind of make this stuff up. We're saying we think this is the answer, negative 14 over 15. And I'd kind of like to have t in it. So I'm going to go back and get rid of that f of x and call it f of t.
Was it negative 4 over 15?
Yeah, 4. Thank you. Not 14. An interesting part of checking your work, like that could have cost me 30 minutes right there. Minus 19 divided by 200. E raised to the negative 5t And then plus 115 divided by 72 e raised to the 3t. So we think that's our answer. We think that's our particular solution. Again, it's kind of fun just to stare at these. And if we went back, I'll do this really quick just because it's kind of, let's do the big picture thing. Remember, if we had done this the traditional way, we would have ended up with a constant in front of these, and we wouldn't have known what it is, right? So remember, this is kind of cool. This is our family of solutions, family of all of our solutions. So that's kind of fun. Whereas we're saying, no, that's actually not, we don't have a family. We've got this one solution right here. Can anybody tell me anything that's good news right here? Clear from the start of this problem? Or maybe bad news? What was our initial conditions? Can I see that bearing?
Comes in at 2. That's good.
Yeah, y of 0 was 2. That's really good. And then y prime of 0 was 5. Now, I can't tell that for sure, but that does look like a fairly steep slope. Of course, I can go over here and cheat and say, what is f prime of 0? It says 5. So that's actually encouraging, is it not? So that's pretty cool. Now, how did I check my work? I'm genuinely trying to recreate this in my mind.
Don't you put in the like our very first non-homogeneous system with the double derivatives?
Yeah, exactly. We want to know if the double derivative plus 2 times the first derivative minus 15 times the function itself is actually equal to 4t minus 8, right? So I'm going to graph the equation y equals 4t minus 8. I'll graph y equals 4x minus 8. So it's like, yeah, there's that guy. And so what we're curious about now, if I just turn this off, is f double prime of t, and then it was plus 2y prime, so plus 2f prime of t,
You did that wrong.
then actually, is it going to like that? I may have to go back and put an x in this. And then minus 15 f of x, or f of t in our case. Oh, I remember what I forgot. Need to graph that. So I need to say y equals that thing. Yes, we got it right. That's a miracle. Notice those are the same graph. So that was how we checked it. Amazing. Cool. So yeah, I find myself thinking kind of the, the same thing as you. Like for instance, if I had some kind of an auto decomposer, if I could take that nastiness that we just decomposed and somehow, run it into some, well, like your generation's version of a calculator. My generation's version of a calculator was what's 56 times 19 when I was really young anyway. But, the modern version is, could I go to Wolfram Alpha or someplace like that and, get it to decompose as we did here? Is there some way I could get that to happen? If there was, that'd be awesome. Because it's not like that's hard. It's just tedious, and you're, likely going to make some dumb mistakes. But the other thing is like, just think about how cool it is. Like all the things to be able to pull that off. Like your ability to kind of work with fractions in a complex way, your ability to use a matrix or solve a system of equations, because we ended up having to solve 2 equations, 2 unknowns down there. And the fact that we've built software to kind of handle that kind of stuff for us. And it's interesting. And as I've often said, because my bent is kind of toward engineering, I just want to get this thing right. Like there's no extra credit in the engineering world for getting this manually. We just want to get it right. So there, I found the model for that bridge or whatever the case may be. And any way I can do that, either faster or, without making a bunch of dumb mistakes that cost me hours trying to catch them and so forth. I'm kind of like, sign me up for that.
How much farther does the math and engineering go?
How much what?
How much farther does the math and engineering go?
Um,
Like, is this
you,
the majority of it?
yeah,
'Cause I
you
know there's
know it
like
all now.
abstract algebra with rings, but I don't know if that gets used.
Yeah, a lot of abstract algebra really has to do with how our algebra system works. It's like the theory behind how algebra works. That's kind of the idea. And I want to say in many respects you're there. And the next project that we're going to do, whatever that is, I'm looking right now. Oh, good, end of the week. Yeah, the next project we're going to do is an engineering problem as well, which is I think
Sweet.
you'll find really cool. And it'll be taking advantage of exactly what we're doing right now. Okay. So tedious. Let's see. So there's a couple other things I got to show you with respect to your assignment, if I remember right. And keep in mind too, because I've had a few people text me with questions and stuff. It's like we're taking 3 days on 7.5. Like every day I'm showing you things you didn't know before. And you, in a sense, won't be able to complete the 7.5 assignment until the end of the day tomorrow, because there's all kinds of little things I got to show you. But let's just pick on this one for now. What if it was a cubed? What if it was a third order differential equation? Let's see, I have an example sitting over here. I wonder if I made up a nice one. I did.
We can do that now.
Except let's put something on the other side. Like, is that terrible? Like, does the Laplace transform swallow that without problem, or is that a problem?
That should be fine.
So notice the pattern. We haven't had a chance to use this, but I included that third derivative on my sheet that I made. But again, notice the pattern. We're to the third power. So it goes s to the third, s to the second, s to the first, and then s to the 0. And then you start out with the Laplace transform of f, which is an integral. You take the derivative of that integral, which means now it's not a derivative. You take the derivative, so it's a first derivative. You take the derivative of that, so it's a second derivative. And the first one is a plus sign, and all the rest of them are minus signs. And so if I understand the pattern here, I don't know as I need to write that one down. Based on that, does it make sense you could solve a 4th, 5th, 6th, 7th, 8th, 9th order differential equation if there was such a thing? I mean, there is in the mathematician's mind, but is there, in the engineer's mind? And the engineer might say, well, it never gets to that. I just need second order differential equations. Incidentally, that last test that I gave you, I haven't taken the time to talk about that, but I gave you a question on there that is really cool. It comes from electrical engineering. And it was a second order differential equation. So, to model how electrical energy works, you got to be able to work with a second order differential equation at times. It's not like you have to do that all the time. And I'd be curious to know, in that world, do they dismiss this in some kind of quick way, or do you actually have to bring all of these skills, to bear? Interesting.
I thought that equation was really cool.
So this actually isn't that bad. It just means we have one more mess to make. What about an initial conditions for this? What initial conditions would I have to give you?
We would need 3.
Yeah, you're actually going to need 3. And you may have saw in that second derivative, or in that Laplace transform of that third derivative a second ago, it had a second derivative in it. So we're actually going to have to know that as well. So let's at least start this. Why don't you, I'll just give you a head start. I'm going to kind of start to catch up to you, but can you write out, can you get yourself to the place where you have the Laplace transform of y equals, and then your big gobbledygook on the other side? not sure I did make that up to work out really nice.
Very nice. So you did throw a 0 in there.
Yeah, some initial conditions I gave you were nice. I don't think I could ever teach again without being able to copy.
I erased something on my whiteboard the other day and tried to hit undo, and it didn't work because it wasn't a computer.
I'm doing this for the sake of the notes as you're doing it with me, but it's not a bad idea even on a test to kind of recheck things yourself, aka, make sure I'm following what you're saying. So check your left side / check my left side. Now I'm thinking, what's the Laplace transform of 16e to the -1t? I think it's 16, and it was over s minus a, but if a is a -1, it'd be s minus a negative, it'd be s plus 1.
I don't know how to simplify that fraction.
Yeah, so generally the rule of thumb, because you want just one big ugly fraction on the right side. So this is a pattern we saw from last time. The fact that I see that I added my 2s to the other side, and then I had a 4 and a -2, which is 2. So I subtracted 2 from the other side. I need to have a common denominator. So I'm looking at this thinking, well, these are over 1. And I need a common denominator. So I got to multiply this top and bottom by s plus 1. So if that's true, I get 16 plus 2s times s is 2s squared. 2s times 1 is 2s. And then minus 2s, 2 times s, and then minus 2 times 1. And that's all over my denominator now of s plus 1. And so I got a little lucky because those two terms just went away. Maybe that's lucky, I don't know. And then, of course, 16 and 2 can go together. So if I divide this over to the other side, then I'll get my s plus 1 down there and all that stuff on top. But all I have on top is 2s squared. 16 minus 2 is 14. So, you know, that's a place I'm going to kind of look on the test. You know, if I see your work and it's like blah, 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 you know, then I'm going to look at this and kind of see, did you get there? And if you didn't, then I go back and kind of look, you know, and see if I can diagnose your mistake, what algebra mistake you made and so forth. But what is it we're always trying to do when we get here?
Look at the denominator, try to find something in our table.
Yeah, we're looking at the denominator and ultimately trying to factor it to get it to be simpler. Like in our last problem, we were able to get the denominator factored all the way down to here. S squared s plus 5s minus 3. And so that allowed us to split it apart into recognizable things. And so I'm thinking the same thing, thinking, how do I factor that? So I like the s plus 1, but I don't like s cubed. And I'm going to have to cheat to factor s cubed. And when I graph that, again, this is a Math 111 concept, but when I graph that, just to save a little time here, there's my cubed graph, and it looks like it crosses at 1. I was hoping it, because it's cubed, I was hoping it would cross at 3 different places, but it looks like it crossed at 1 only. And notice I see the cubed, so I know it's not going to do anything interesting outside of my window. I see the little hoop-de-doo, the little S shape in it, so I know it crosses at 1, and that's it. So that tells me, let's go ahead and do this the cool way. Since it crosses at 1, then let's do synthetic division. Do you remember this? I just took the coefficients from here, 1, 1, 3, -5. And I bring the first one down. 1 times 1 is 1. I add those, I get 2. 1 times 2 is 2. 3 plus 2 is 5. 1 times 5 is 5. Of course, I got 0 there because the graph told me 1 was an answer. Now, in a sense, I got a little lucky because it could have been 0.999 and it just looked like 1. But of course, there's a 0 there. So what does that mean? And as an example, synthetic division is something you probably can't do right now, right? Like that was a long time ago and I can't do it. So can you do long division? You should still be able to do long division, but that's again why I'm always teaching from the perspective of like understand the logic. Shortcuts are really cool, but you're going to forget them. So what this tells me is that this thing does indeed factor to s minus 1, but more importantly, this tells me what's left. In other words, 1s squared plus 2s plus 5. The graph tells me, because it only crossed once, again, these are all algebra math 111 ideas, but the graph tells me the rest of this doesn't factor. Do you understand why? If it did factor, then I would have saw it hit the graph 2 more times. But it didn't. So I know that doesn't factor. And then when I stare at it, I can kind of, because it's so small, 2 and 5, I can kind of think, oh yeah, I can tell that doesn't factor.
Is this supposed to be S plus 1?
No, because the 0 was 1.
Oh, okay, okay.
Yeah, and that's not obvious. I'm glad you said that. So that's as far as this thing will factor, which means now I got to go to work splitting it up. So how's this going to split up? Well, because S minus 1 is just an S, then that means just a constant above it will work. S squared plus 2S plus 5 doesn't factor, but because it's S squared, then that means I need an S term above it, one lower, and I'll need the constant that goes with it. And then this last one is just an S term. I think this is what that's going to break down to. So what I'm trying to do is force that to be equal to the denominator. I'm not going to rewrite that.
Like you wrote S plus 1, is that S minus 1?
No, because I had an S plus 1 originally.
Oh, I see where you got
And
it.
then when
Okay,
I
cool.
factored this green equation, I had an S minus 1 and the rest of that. got
Okay.
Yeah, that's what I saw too.
I know. I was like, so you're saying Raymond's right now?
So again, this is horrible because what's my next move?
Multiply by common denominator, the top and bottom.
Exactly. So this is going to need an S plus 1. And it's also going to need an S squared. And we won't have time to finish this. I'll probably just finish it and stick it in the notes for you to look at. But man, my S's look like 5s. It's horrible. And this is going to need an S plus 1 and an S minus 1. And this will need everything that it doesn't have, which of course means it needs an S minus 1 and an S squared plus 2S plus 5. Yeah, maybe I won't. Maybe I'll just finish this tomorrow because I kind of would, we still need practice with this. I don't think you need me to help you with figuring out A, B, C, D here. I think you can do that, but we still need a little bit of practice with decomposing this one. Like if this ended up 7 over S minus 1, oh yeah, that's 7e to the t. I got that. I know how to Laplace that, but we're not very good at this one yet, right? We've only done one of those. And so that again looks like one of those, well, is this going to be a complete the square and a sine cosine? Is it going to go down that road? My advice to you would be finish this yourself, and then I'll sort of quickly finish it with you tomorrow. I'll copy this onto the next note sheet or something, and we'll just take it from there so that you can actually watch that happen and hopefully feel a sense of satisfaction like you got it. But I think it'd actually be good for me not to end up I always catch up to you and end up finishing before you. I think it might be good for you to see if you can finish that and then go check it. Like go check and see if it actually worked. Go satisfy yourself that you got this. But of course you should have a sense of like, wow, we're taking a test Monday. This is like an hour-long question. If you don't even make any dumb mistakes, it's an hour and a half if you do. So again, I'm very aware of that as a teacher. I either have to give you not very many problems or Well, let's not give them a cubed one, right? I mean, that's an option. Like make sure it kind of stays kind of mellow here. I don't want it to go out of control. Yeah, let's do that.
So Doug, tomorrow are we gonna go over like how to change initial conditions and things like that?
Yeah, so the one thing you don't, there's one question in your assignment where the initial conditions are, what if the initial condition isn't at time 0, but what if it's at like time 2? Which is, again, that's not something an engineer would do, but that's something a mathematician would do. You know, what if that 0 was like a 2? At time 2, it was at 0. And at time 2, its speed was this. And at time 2, its change of speed was this. What are we going to do then? Because if that's the case, then doesn't it mean this isn't going to work? Because these have y of zeros in them, right? So that seems like, so if you're, slowly kind of working on your 7.5 assignment, I wouldn't do that question until
I feel
I
like
get a
that.
chance to show you that tomorrow.
I feel like there'd be a lot of engineering stuff around that.
Exactly. In the sense that, if you're collecting data, maybe you don't know what happened at time 0. Like you turned on the tank and then you said, whoa, it's blowing up or whatever. And so you went out and measured it. But then that was like at time 6, 6 minutes later, I, took a reading and the temperature was this. And so I didn't know the time. I didn't know the temperature at the initial. So could we still survive that? It's really cool that you can. So that's question 14 in your assignment. So it's kind of easy to get around, but it kind of takes me showing you something kind of cool to get there for reading the book. So yeah, we actually still have things to talk about in 7.5. So I'll still post these notes for today, even though we haven't finished this question. We'll finish it tomorrow.
Thanks, Doug. Have a good morning.
You as well.
Thank you, Doug.
All right. Thanks, Doug.
Thank you.
Thank you all.
See ya.
I just had a question about number 10 on 7.3.
Okay.
I think so we're supposed to use these two tables, 7.1 and 7.2, to determine the Laplace transform of the given function. And I think I'm getting thrown off because it's t times e to the 2t times cosine of 5t. So it's like 3 functions multiplied together.
Yeah, that's exactly right. I'm just reading the directions to make sure I'm.
Mhm.
Yeah, so if you look at table 7.2, are you looking at your book?
Yeah.
Look at the very last one. That very last one is the shortcut I showed you today, which is how to get rid of t. So in number 10, when you're sitting there looking at t times e to the 2t times cosine of 5t, what I showed you today is a way you can just say, yeah, let's just not have the t. T's gone. Or
Okay.
you could get rid of the e, right? Or
Okay.
other, what I called in my note sheet, cool dodge, which is the third one down on table 7.2. You could get rid of the e. And then it would just be t cosine of 5t.
Okay. Yeah, I see that now.
Or perhaps both. So yeah.
Yeah, I'm definitely going to be reviewing 7.2 stuff from last week and then yesterday's lecture as well, because this is really, really intense.
Yeah, it's pretty heady, isn't it?
Yeah.
We are way out in the universe right now. There's no other people out here.
That's how it feels.
Yeah, well, feel free to hit me up outside of class. I know your situation is kind of challenging in that regard, not being able to take it in live and all that. I mean, you're still able to watch the video, of course. But.
Okay. Yeah, I'll go over it. And then maybe tomorrow after my speech class, which we'll get out at 3:30, I might want to meet up after that time, if that's okay.
Yeah, I don't see why not. Just hit me up. I don't know what I got going tomorrow, but generally I'm either kayaking or sitting at my desk. So
Okay, yeah, I'll let you know earlier in the afternoon, right at the
Okay.
last minute.
yeah,
All
I'll
right.
text you and we'll make a plan.
All right. See you later, Doug.
See you later.